Hello and welcome back. In this video we're going to further our discussions in Chapter 16 on oscillatory motion and waves. In the last lecture we began discussing the mass spring system and the different quantities involved to fully be able to describe the oscillatory repetitious motion of the mass spring system as it oscillates to and fro. In this video we're going to talk about the simple pendulum. So I've drawn here a pendulum on the board. There's the bob that hangs at the end of the pendulum, which I have drawn as a circle, and it has a certain mass m. The length of the string is L, and theta is the angle that the string makes with the vertical. Notice this is the equilibrium position for the mass. When we place the mass in that position and let go, there's no motion. But when we pull the mass away from its equilibrium position, it begins to sway to and fro. Oscillatory motion. So when we look at a free body diagram for this mass, when it's someplace in its motion, we can say that it's rising up, for example. As it's rising up, there are two forces that act on it. There's the tension force that is always directed along the string that pulls on M. So it's pointing in this direction. And then there's the force of gravity provided by the Earth's gravitational field that is pointing straight down into the center of the Earth. I can resolve mg into component pieces that are centripetal and tangential. Mg sine theta is tangent to the motion. And mg cosine theta is centripetal or radial, lies along a line that goes through the center of the circle. Remind yourself, we discussed this back in Chapter 7, but the pendulum is tracing out an arc of a circle, so it's undergoing circular motion all the time. So the tension force and mg cosine theta are both radial or centripetal forces, so I can sum them up and set them equal to the mass times the centripetal acceleration. Remember, centripetal acceleration is the speed squared over the radius of the circle. The radius of the circle is the length of the string, so L is the radius of the circle. Writing the tangential equation, I have minus mg sine theta is equal to m times a tangential. Now, why the negative sign? Well, we need to consider what goes on with theta. When theta is measured on this side, theta is positive, and when theta is measured on this side, theta is negative. So when theta is negative, mg sine theta is pointing in the positive direction. When theta is positive, mg sine theta is pointing in the negative direction. So they should have different signs. And so that is where the negative sign comes from, is that mg sine theta is a restoring force. It's always trying to point back to the equilibrium position. So the entire time the mass is to the left of the equilibrium position, the force is pointing to the right. Every time the mass is to the right of the equilibrium position, the restoring force is pointing to the left. So it's known as a restoring force, and this form of an equation is a restoring force equation. So notice that the m's cancel on both sides of the equation, and I get minus g sine theta is equal to a tangential. So now what we'll do is simplify our analysis by considering only angles that are small. And when I say small angles, these are angles that are less than 15 degrees. And 15 degrees in radians is 0.26 radians. So for small angles, the sine of theta is about the same as theta. You can try this in your calculator. You need theta in radians for this formula to show its true nature. You can put in the sine of 0.26 radians, and you'll get approximately 0.26 as the answer. So this formula holds for theta in radians. And so we're going to live within the small angle approximation, and when we do that, then we can replace sine theta with just theta. So this equation here becomes minus g theta is equal to a tangential. Now we're going to use a principle that we learned back in Chapter 10, or a relationship that we learned back in Chapter 10. The tangential acceleration is equal to the angular acceleration times the radius of the circle. So recall that alpha is angular acceleration, and you can remind yourself by going back and looking in chapter 10 what alpha is defined as. And so using that and substituting A tangential as alpha L, we get minus G theta is equal to alpha L. So we can solve this equation, and that tells us, and again, this is a differential equation. Alpha is the second time derivative of theta. So this is a differential equation that we are not yet equipped to solve. You'll have to trust me that the solution is that theta, as a function of time, this angle, which is constantly changing, right, as a function of time, as this pendulum exhibits oscillatory motion, is given by the maximum angle. So this would correspond to maybe the mass pulled out that I release from some maximum angle. That would be the maximum angle times the cosine of the square root of G on L times time. So this entire expression is in the argument of cosine. So, and it's a little bit of a mess. My apologies. I should have put parentheses around it when I was placing it up here. So let's do it like this, and then this is from chapter 10. So again, recall that the argument of cosine, sine, tangent must be units of radians. So I've got time here. So that means the square root of G on L must be radians per second, and radians per second is our angular frequency. So omega for the simple pendulum is the square root of G on L. That's angular frequency. The frequency then is omega over 2 pi. And so if I take square root of G on L and divide by 2 pi, I get 1 on 2 pi square root G on L. So this is the frequency. Notice that the acceleration due to Earth's gravity is scaling directly as the frequency, or the square root of the acceleration due to Earth's gravity is scaling as the frequency. And the square root of the length of the string is scaling inversely as the frequency. I can also solve for the period by just inverting the frequency. So when I invert this side, I get 2 pi square root of L on G. So this gives us these frequencies, angular frequencies, and periods for the simple pendulum. And so now we know the mass spring system and the simple pendulum. And in the next video, we'll pick a problem from the back of chapter 16 to apply these concepts to something that you will be seeing as you work through your problems. So we'll see you next time.